Welcome to Applied Linear Algebra for Machine Learning Engineers. Linear algebra is a field of mathematics that's universally agreed upon to be a prerequisite for a deeper understanding of machine learning. Although linear algebra is a large field with many esoteric theories and findings, the nuts and bolts tools and notations taken from the field are practical for machine learning practitioners. With a solid foundation of what linear algebra is, it's possible to focus on just the good and relevant parts. Linear algebra textbooks are going to teach you linear algebra in the classical university bottom-up approach. This is too slow and painful for the needs of a machine learning practitioner. Like learning machine learning itself, we're going to take the top-down approach. Rather than just starting with theorems and abstract concepts, you're going to learn the basics of linear algebra in a concrete way, with data structures and worked examples of operations on those data structures. It's so much faster. Once you know how the operations work, you can circle back and learn how they were derived. In this course, you're going to discover what linear algebra is, and the focus of the course is going to be linear algebra from the perspective of machine learning. Thanks for your interest in applied linear algebra for machine learning engineers. Let's get started. Hello and welcome back. Now you might be thinking, why do I want to study linear algebra? Well, you might not want to, but in order to become a machine learning engineer, it's probably a good idea. Number one, it's a building block. Linear algebra is absolutely key to understanding the calculus and statistics you're going to need in machine learning. Becoming better at linear algebra will lift your game across the board. Number two, you're going to have a deeper intuition. If you can understand machine learning methods at the level of vectors and matrices, it's going to improve your intuition on how it all works and how it all fits together. Number three, you're going to get more from algorithms. A deeper understanding of the algorithm and its constraints will allow you to customize its applications and help you better understand the impact of tuning parameters on the results. Fourthly, you can implement your own algorithms from scratch. You require an understanding of linear algebra to implement machine learning models from scratch. At the very least, you're going to need to read the algorithm's description, and at the best, to effectively use libraries that provide the vector and matrix operations. Fifthly, devise new algorithms. The notation and tools of linear algebra can be used directly in environments like Octave and MATLAB, allowing you to prototype modifications to existing algorithms and entirely new approaches very quickly. Linear algebra will weigh heavily on your machine learning journey. Linear algebra is a field of mathematics that's universally agreed upon to be a prerequisite for a deeper understanding of machine learning. Although linear algebra is a large field with many esoteric theories and findings, the nuts and bolts and tools and notations taken from the field are practical for machine learning practitioners. With a solid foundation of what linear algebra is, it is possible to focus on just what's relevant and the good parts, so to speak. In this lesson and the next few, you're going to discover exactly what linear algebra is from a machine learning perspective. So this lesson and the next few are going to be divided into four parts. Number one, we're going to talk about linear algebra. Number two, we're going to talk about numerical linear algebra. Number three, we're going to talk about linear algebra and statistics. And number four, we're going to talk about the applications of linear algebra. All right, let's get started by talking about linear algebra. Firstly, linear algebra, as we've noted already, is a branch of mathematics. But the truth is, linear algebra is the mathematics of data. Matrices and vectors are the language of data. Linear algebra is all about linear combinations, that is, using arithmetic on columns and numbers called vectors and arrays of numbers called matrices to create a new column and array of numbers. Linear algebra is the study of lines and planes, vector spaces, and mappings that are required for linear transformations. It's a relatively young field of study, having initially been formalized in the late 1800s in order to understand unknown systems of linear equations. A linear equation is just a series of terms of mathematical operations, where some of the terms are unknown. For example, we have one on screen. Equations like this are linear in that they describe a line on a two-dimensional graph. The line comes from plugging in different values into the unknown x to find out where the equation or the model does to find the value y. We can line up a system of equations with the same form with two or more unknown values, for example, as shown on screen. The column of y values can be taken as a column of vectors of outputs from the equation. The two columns of integer values are the data in the column, say A1 and A2, and can be taken as a matrix of A. The two unknown values, x1 and x2, can be taken as the coefficients of the equation and together form a vector of unknowns b to be solved. You can write this equation compactly in a linear algebra notation as y equals a of b. Problems of this form are generally challenging to solve because there are many unknowns. Here we have 2. Then there are equations to solve, but here we have 3. Further, there is often a single line that can satisfy all the equations without error. Systems describing problems we are often interested in, such as linear regression, can have an infinite number of solutions. This provides you with a small taste of a very core of linear algebra that interests us in machine learning. Most of the rest of the operations are about making this problem and these problems like this easier to understand and solve. Next up, let's talk about numerical linear algebra. The application of linear algebra in computers is often called numerical linear algebra. Numerical linear algebra really just means applied linear algebra. It's more than just the implementation of linear algebra operations in code and libraries. It also includes the careful handling of the problems of applied mathematics, such as working with limited floating point precision of digital computers. Computers are good at performing linear algebra calculations, and much of the dependence on graphical processing units by modern machine learning methods, such as deep learning, is because of their ability to compute linear algebra operations fast. Efficient implementations of vector and matrix operations were originally implemented in the Fortran programming language in the 1970s and the 1980s, and a lot of code, or code ported for those implementation, underlies much of the linear algebra form using modern programming languages today, such as Python. 3 popular open-source numerical linear algebra libraries that implement these functions are the Linear Algebra Pack, or LAPACK, Basic Linear Algebra Subprograms, or BLAS, and Automatically Tune Your Linear Algebra Software, or ATLAS. Often, when you're calculating linear algebra operations directly or indirectly via high-order algorithms, your code is very likely dipping down into one of these, or a similar linear algebra library. The name of one or more of the underlying libraries may be familiar to you if you have installed or compiled any of the Python's numerical libraries, such as SciPy or NumPy. Alright, let's briefly touch on linear algebra and statistics. Linear algebra is a valuable tool in other branches of mathematics, especially statistics. The impact of linear algebra is important to consider, given the foundational relationship between both fields, as they have in the field of applied machine learning. Some clear fingerprints of linear algebra in statistics and statistical methods include the use of vector and matrix notation, especially with multivariate statistics, solutions to least squares and weighted least squares, such as a linear regression problem, estimates of mean and variance of data matrices, the covariance matrix that plays a key role in multinomial Gaussian distributions, principal component analysis for data reduction that draws on many of the elements together. Modern statistics and data analysis, at least as far as the interest of machine learning practitioners are concerned, depend on the understanding of the tools of linear algebra. Alright, let's briefly touch on the applications of linear algebra. A linear algebra is a mathematics of data. The tools of linear algebra are used in many domains. Let's talk about a few. Matrices in engineering, such as a line of springs, graphs and networks, such as analyzing networks, Markov matrices, population, and economics, such as population growth, linear programming, the simplex optimization method, Fourier series, linear algebra for functions, used widely in signal processing, linear algebra for statistics and probability, such as least squares for regression, computer graphics, such as various translations, rescaling, and rotation of images. Another interesting application of linear algebra is that it's a type of mathematics used by Albert Einstein and parts of his theory of relativity, specifically tensors and tensor calculus. He also is responsible for introducing a new type of linear algebra notation to physics, called Einstein notation, or the Einstein summation convention. Welcome to this introduction to NumPy arrays. Arrays are the main data structure used in machine learning. Arrays from a library called NumPy, or called n-dimensional arrays, or ND arrays, are used as a primary data structure for representing data. In this lesson and the next few, you're going to discover the n-dimensional array in NumPy for representing numerical data, and then for manipulating data in Python. This lesson and the next few is going to be broken into 3 parts. Firstly, we're going to look at the NumPy n-dimensional array. Secondly, we're going to look at functions to create arrays. And then 3, we're going to combine some arrays. Alright, let's get started. NumPy is a Python library that can be used for scientific and numerical applications, and it's a tool for linear algebra operations. NumPy is numerical Python. The main data structure in NumPy is the ND array, which is a shorthand name for an n-dimensional array. When working with NumPy, data in an ND array is simply referred to as an array. It's a fixed-size array in memory that contains data of the same type, such as integers or floating point values. The data type supported by arrays can be accessed via the dType attribute on the array. The dimensions of an array can be accessed via the shape attributes that returns a tuple describing the length of the dimensions. There are a host of other attributes. A simple way to create an array from data, or simple Python data structures, like a list, is to use the array function. Our example on screen creates a Python list of 3 floating point values, then creates an int array from the list, and then we access the array shape in the data type. When we execute the code, it prints the contents of the int array, the shape, which is a one-dimensional array with 3 elements, and the data type, which is a 64-bit floating point. Next up, we've got functions to create arrays. There are more convenience functions for creating fixed arrays that you may encounter or be required to use. Let's look at a few. First, the empty function will create a new array of a specified shape. The argument to the function is an array or tuple that specifies the length of each dimension of the array to create. The values or content of the created array will be random and will need to be assigned before you use them. The example on screen creates an empty 3x3 two-dimensional array. Executing the code prints out the contents of the empty array. Your results are going to vary. Next up, there are zeros. The zero function will create a new array of a specified size with its contents filled with the 0 values. The argument of the function is an array or tuple that specifies the length of each of the dimensions to create for the array. The example on screen creates a 3x5 zero-dimensional array. Executing the code prints our array of lots of zeros. Next up are ones. The ones function will create a new array of a specified size with the contents filled with 1 values. The argument to the function is an array or tuple that specifies the length of each dimension of the array to create. Again, our example on screen creates a 5-element one-dimensional array. Next up, let's talk about combining arrays. NumPy provides many functions to create new arrays from existing arrays. Let's look at 2 of the most popular functions you may need or encounter. Number 1, the vertical stack. Given 2 or more existing arrays, you can stack them vertically using vstack. For example, given 2 one-dimensional arrays, you can create a new one-dimensional array with 2 rows by vertically stacking them. The code for this is demonstrated on screen. Running the example first prints the 2 separately defined one-dimensional arrays. The arrays are then vertically stacked, resulting in a new 2x3 array, the contents in the shape which are then printed. Next up, we have horizontal stacking. Given 2 or more existing arrays, you can then stack them horizontally using the hstack function. For example, given one-dimensional arrays, you can create a new one-dimensional array, or 1 row within the columns of the first and second arrays concatenated. This example is also demonstrated on screen. When we execute the code, the example first prints the 2 separately defined one-dimensional arrays. The arrays are then horizontally stacked, resulting in a new one-dimensional array with 6 elements, the contents in the shape which are then printed out. Hello and welcome back. Now let's go ahead, index, slice, and reshape our NumPy arrays. Machine learning data is represented as arrays. In Python, data is almost universally represented as NumPy arrays. If you're new to Python, you may be confused by some of the Pythonic ways of accessing data, such as negative indexing and array slicing. In this lesson and the next few, let's go ahead and discover how to manipulate and access your data correctly in NumPy arrays. Let's talk about the one-dimensional list to array. You may load your data or generate your data and have access to it via a list. You can convert a one-dimensional list of data to an array by calling the array function in NumPy. When we execute the code, it prints out the list to the NumPy array. Now, it's more likely in machine learning that you're going to have a two-dimensional data array. That is a table of data where each row represents a new observation and each column is a new feature. Perhaps you generated the data or loaded it using custom code, and now you have access to the list of lists. Each list represents a new observation. You can convert your list of lists to a NumPy array the same way as above by calling the array function, as shown on screen. When we execute our code, you can see it prints out our NumPy array. All right, let's talk about array indexing. Once your data is represented using a NumPy array, you can access it using indexing. Let's look at some examples of accessing data via indexing. First, let's talk about a one-dimensional index, or one-dimensional indexing. Generally, indexing works just like you would expect from your experience with other programming languages like C, Java, C#, and so on. For example, you can access elements using the bracket operator, then by specifying the 0 offset index for the value to retrieve. We have an example on screen, and when we execute it, it prints the first and last values in the array. If you specify integers that are too large for the bound of the array, it's going to cause an error, again as shown on screen. One key difference is that you can use negative indexes to retrieve values offset from the end of the array. For example, the index -1 refers to the last item of an array. The index -2 returns the second and last item to the array. So you work your way back all the way to -5 for the very first item in the current example. Again, our example shown on screen, and when you execute it, it prints the last and the first items in the array. Next up, two-dimensional indexing. Indexing two-dimensional data is similar to indexing one-dimensional data, except that the comma is used to separate the index from each dimension. Now, this is different from C-based flavor languages, where a separate bracket operator is used for each dimension. For example, we can access the first row and the first column as shown on screen. Executing the example prints the first item in the dataset. If you're interested in all the items in the first row, you can leave the second dimension index empty, for example, as shown on screen. All right, next up, let's talk about array slicing. So far, so good. Creating and indexing arrays looks familiar. Now we come to array slicing, and this is one of the features that causes problems for beginners to Python and NumPy arrays. Structures like lists and NumPy arrays can be sliced. This means that a sequence of a structure can be indexed and retrieved. This is most useful in machine learning when specifying input variables and output variables, or splitting training rows for testing rows. Slicing is specified using the colon operator, with a from and to index before and after a column respectively. The slice extends from the index and ends with one item to the index. Let's look at a one-dimensional slice. You can access all the data in an array dimension by specifying the slice with a colon, with no index. We have an example on screen. Running this example prints all the elements of the array. The first item of the array can be sliced by specifying a slice that starts at index 0 and ends at index 1, one item before the to index. Again, we have an example on screen, and when we execute the code, it returns the subarray with the first element. We can also use negative indexes in slices. For example, we can slice the last two items in the list by starting at slice number -2, the second from the last item, and not specifying the to index, the word to, that takes the slice at the end of the dimension. We have an example of this on screen, and when we execute it, it returns the subarray with the last two items only. Next up, we have two-dimensional slicing. So let's look at some examples of two-dimensional slicing, which is something you're going to see often in machine learning. All right, let's go ahead and split the input and output features. It's common to split your loaded data into input variables x and an output variable y. We do this by slicing all rows and all the columns up to, but before the last column, and then by separately indexing that last column. For the input features, we can select all the rows and all the columns except the last one by using the colon for the rows in the index, and a -1, or a colon -1, in the columns of the index. For the output column, we can select all the rows again by using the colon and index just the last column by specifying the -1 index. All right, let's put all this together. We can separate a 3-column two-dimensional data set into input and output values, as shown on screen. Running the code prints the separated x and y elements. Note that the x is a two-dimensional array, and the y is a one-dimensional array. All right, let's go ahead and split and test the rows. It's common to split a loaded data set into separate training and testing sets. This is a splitting of the rows where some portion will be used to train the model, and the remaining portion is going to be used to estimate the skill of the trained model. This will involve slicing all columns by specifying the colon in the second dimension of the index. The training data set would be all the rows from the beginning to the split point. The test data set would be all the rows from starting at the split point to the end of the dimension. All right, let's put this together. We can split the data set at the contrived split point of 2, as shown on screen. When we execute the example, it selects the first 2 rows for training, and then the last 2 for the test set. Next up, let's cover array reshaping. After slicing your data, you may need to reshape it. For example, some libraries, such as scikit-learn, may require that a one-dimensional array for output variables y be shaped as a two-dimensional array with one column, and outcomes for each column. Some models or algorithms, like short-term recurrent neural networks, and Keras require the input to be specified as a three-dimensional array comprised of samples, timestamps, and features. It's important to know how to reshape your NumPy arrays so that your data meets the expectations of the specific Python libraries and the various models. All right, let's look at some examples. NumPy arrays have a shape attribute that returns a tuple of the length of each dimension for the array. An example's on screen. When we execute the code, it prints a tuple for one dimension. Next up, we have a tuple with two lengths as returned for a two-dimensional array. You can use the size of your array dimensions in the shape dimension, such as specifying parameters. The elements of the tuple can be accessed just like an array, with the 0th index for and the first index for the number of columns. We have an example of this on screen, and when we execute the code, it gives the specific sizes for each dimension. All right, let's reshape a 1D to a 2D array. It's common to need to reshape one-dimensional arrays into two-dimensional arrays with one column and multiple arrays. NumPy provides a reshape function on the NumPy array object that can be used to reshape your data. The reshape function takes a single argument that specifies a new shape of an array. In the case of reshaping a one-dimensional array into a two-dimensional array with one column, the tuple would be the shape of the array as the first dimension, and 1 for the second. Let's put this together, and on screen we have an example. When we execute the code, it prints the shape of the one-dimensional array, reshapes the array into 5 columns with one column, then prints the new shape. Let's go ahead and reshape a 2D array to a 3D array. It's a common practice to reshape two-dimensional data, where each row represents a sequence into a three-dimensional array for algorithms that expect multiple samples of one or more time steps and one or more features. A good example is an LSTM recurrent neural network model in Keras for deep learning. The shape function can be used directly, specifying new dimensionality. This is clear with an example where the sequence has multiple time steps with an observation, a feature. We can use the sizes of the shape attribute on the array to specify the number of samples, the number of rows, and columns, the time steps, and fix the number of features at 1. Putting all this together, we have an example on screen. When we execute the code, it first prints the size of each dimension of the 2D array, it reshapes the array, and then it summarizes the shape of the new 3D array. Hello, welcome back. On to NumPy array broadcasting. Arrays with different sizes can't be added, subtracted, or generally used in arithmetic. A way to overcome this is to duplicate the smaller array so that it has the dimensionality and the size of the larger array. This is called array broadcasting, and it's available in NumPy when performing array arithmetic, which can greatly reduce and simplify your code. In this lesson, and perhaps the next few, we're going to discover array broadcasting and how to implement it in NumPy. This section and the next few lessons are broken into 4 disparate parts. Firstly, limitation with array arithmetic. Secondly, array broadcasting in NumPy, and then fourth, the limitations of broadcasting. Let's start off with the limitation of array arithmetic. You can perform arithmetic directly on NumPy arrays, such as addition and subtraction. For example, 2 arrays can be added together to create a new array, where the values at each index are added together. For example, an array can be defined as 1, 2, 3, and array B can be defined as 1, 2, 3, and then adding these together will result in a new array, 2, 4, 6. Strictly speaking, arithmetic may only be performed on arrays that have the same dimensions and dimensions with the same size. This means that a one-dimensional array with a length of 10 can only perform arithmetic with other one-dimensional arrays with a length of 10. This limitation on array arithmetic is quite limiting. Thankfully, NumPy provides a built-in workaround to allow arithmetic between arrays with differing sizes. All right, let's discuss array broadcasting. Broadcasting is a name given to the method that NumPy uses to allow arithmetic between arrays with different shapes and sizes. Although the technique was developed for NumPy, it's also been adopted more broadly in other numerical computational libraries, such as Theano, TensorFlow, and Octave. Broadcasting solves the problem of arithmetic between arrays of differing shapes by in effect replicating the smaller array along the last mismatched dimension. NumPy doesn't actually duplicate the smaller array. Instead, it makes an end memory and a computationally efficient use of existing structures that in effect achieve the same result. The concept has also permeated linear algebra notation to simplify the explanation of simple operations. All right, now we have some definitions and some theory out of the way. Let's get to some concrete examples. We're going to look at 3 different examples. First, we're going to start out with scalar and one-dimensional arrays. A single value, or a scalar, can be used in arithmetic with a one-dimensional array. For example, we can imagine a one-dimensional array A with three values of A1, 2, and 3, and add it to scalar B. The scalar will need to be broadcast across the one-dimensional array by duplicating the value 2 more times. The two-dimensional arrays can then be added directly. The example on screen demonstrates this. Running the code first prints the defined one-dimensional array, then the scalar, followed by the result where the scalar is added to each value in the array. Next up, a scalar in a two-dimensional array. A scalar value can be used in arithmetic with the two-dimensional array. For example, we can imagine a two-dimensional array A with 2 rows and 3 columns added to a scalar B. The scalar needs to be broadcast across each row of the two-dimensional array by duplicating it 5 more times. The two-dimensional array can be then added directly. The complete example is on screen. When we execute the code, it first prints the defined two-dimensional array, then the scalar, then the result of the addition of the value 2 added to each value in that array. Next up, we have one-dimensional and two-dimensional arrays. A one-dimensional array can be used in arithmetic with a two-dimensional array. For example, we can imagine a two-dimensional array A with 2 rows and 3 columns added to a one-dimensional array B with 3 values. The one-dimensional array is broadcast across each row of the two-dimensional array by creating a second copy to result in a new dimension B. The two-dimensional arrays can then be added together. Running the example first prints the defined two-dimensional array, and then the defined one-dimensional array, followed by the result C, where in effect each value in the two-dimensional array is doubled. Alright, let's talk about some of the limitations of broadcasting. Broadcasting is a handy shortcut that proves to be very useful in practice when working with NumPy arrays. That being said, it does not work for all classes, and in fact it imposes a strict rule that must be satisfied for broadcasting to be performed. Arithmetic, including broadcasting, can only be performed when the shape of each dimension in the arrays are equal or one has the dimension size of 1. The dimensions are considered in reverse order, starting with the trailing dimension. For example, looking at columns before rows in a two-dimensional case. This makes more sense when we consider that NumPy will in effect pad missing dimensions with the size of 1 when comparing arrays. Therefore, the comparison between a two-dimensional array A with 2 rows and 3 columns and a vector of B with 3 elements looks like what we have on screen. In effect, this becomes a comparison between the example shown on screen. The same notion applies to the comparison between a scalar that is treated as an array with the required dimensions, and again the example is on screen. This becomes a comparison between, again the example is on screen. When the comparison fails, the broadcast cannot be performed and an error is raised. The example on screen attempts to broadcast a 2-element array to a 2x3 array. This comparison in effect is, again the example shown on screen. We can see that the last dimension, the columns, do not match, and we would expect the broadcast to fail. The example below demonstrates this in NumPy. When we execute the code, it first prints the shapes of the arrays and then raises an error when attempting to broadcast, as we expected. Hello and welcome back. Let's start talking about vectors and vector arithmetic. Vectors are a foundation element of linear algebra. Vectors are used throughout the field in machine learning in the description of algorithms and the processes such as the target variable y when training a model. Model and algorithm are synonymous terms here. In this lesson and the next few, we're going to talk about linear algebra vectors for machine learning. As always, we're going to break this down into subsections. Firstly, we're going to ask the question, what is a vector? Secondly, we're going to define a vector. Thirdly, we're going to talk about vector arithmetic. Fourthly, we're going to discuss vector dot product. And fifthly, we're going to talk about vector scalar multiplication. All right, so let's tackle that first one. What is a vector? A vector is a tuple of one or more values called scalars. Vectors are often represented using a lowercase character such as a v. For example, the expression shown on screen, where v's of 1, 2, and 3 are scalar values, often real values. Vectors are also shown using a vertical representation of a column, again as shown on screen. It's column to represent the target variable as a vector with a lowercase y when describing the training of machine learning algorithm. It's also common to introduce vectors using a geometric analogy, where a vector represents a point or a coordinate in an n-dimensional space, where n is the number of dimensions, such as 2. A vector can be thought of as a line from the origin of the vector space with a direction and a magnitude. These analogies are a good starting point, but should not be held too tightly, as we often consider very high-dimensional vectors in machine learning. Alright, now that we know what a vector is, let's look at how to define a vector in Python. Alright, let's look at some code when we define a vector. We can represent a vector as a NumPy array in Python. A NumPy array can be created from a list of numbers. For example, on screen we define a vector with a length of 3 and an integer value of 1, 2, and 3. The example defines a vector with 3 elements, and it returns the output 1, 2, 3. Alright, let's delve into some vector arithmetic, where all the operations provided element-wise to 2 vectors of equal length that will result in a new vector with the same length. Alright, so we have 2 vectors of equal length can be added together to create a new vector. The new vector has the same length as the old 2 vectors. Each element of the new vector is calculated as the addition of the elements of the other vectors at the same index. An example is shown on screen, or put it another way, we've simply defined it a different way, again as shown on screen. We can add vectors directly in Python by adding NumPy arrays. The example defines 2 vectors with 3 elements each, and then adds them together. We execute the code, it prints the 2 parent vectors, and then it prints a new vector that is the addition of the 2 vectors. Alright, let's do a quick vector subtraction. One vector can be subtracted from another vector of equal length to create a new third vector. As with addition, the new vector has the same length as the parent vector, and each element of the new vector is calculated as the subtraction of the element at the same indices. The example to show it a different way is shown on screen. The NumPy arrays can be directly subtracted in Python. Our example on screen defines 2 vectors with 3 elements each, then subtracts the first from the second. When we execute the code, it prints the vectors and then prints the new vector that is first minus the second. Alright, let's wrap this up talking about vector dot product. We can calculate the sum of multiplied elements of 2 vectors of the same length to give a scalar. This is called a dot product, named because the dot operator used when describing the operation. The operation can be used in machine learning to calculate the weighted sum of a vector. The dot product is calculated as follows. We can calculate the dot product between 2 vectors in Python using the dot function on a NumPy array. Let's go ahead and look at a complete example. The example defines 2 vectors with 3 elements each, then calculates the dot product. Running the code first prints the 2 parent vectors, then the scalar dot product. A vector can be multiplied by a scalar, and affects scaling the magnitude of the vector. To keep the notation simple, we're going to use the lowercase s to represent the scalar value, or c equals sv. The multiplication is performed on each element of the vector. That results in a new scaled vector of the same length. We're going to perform this operation directly with NumPy arrays, as shown on screen. When we execute the code, it defines the vector and the scalar, and then multiplies the vector by the scalar. You can see it first prints the parent vector, then the scalar, then the results of multiplying the 2 together. Similarly, vector scalar addition, subtraction, and division can be performed in the same way. Hello and welcome back. Now we're going to talk about vector norms in machine learning. Calculating the length or magnitude of vectors is often required either directly as a regularization method in machine learning, or as part of a broader vector or matrix operations. In this lesson, and perhaps the next few, you're going to discover how to calculate vector lengths and magnitudes, called the vector norm. As we've seen already, we're going to divide this into 4 sections. We're going to divide it into understanding the vector norm. Number 2, the vector L1 norm. Number 3, we're going to talk about the vector L2 norm. And then lastly, we're going to talk about the vector max norm. All right, let's dive in by talking about the vector norm. Calculating the size or length of a vector is often required either directly or as a vector matrix operation. The length of a vector is referred to as its vector norm or its vector magnitude. The length of a vector is always a positive number, except for a vector of all 0 values. It's calculated using some measure that summarizes the distance of the vector from the origin of the vector space. For example, the origin of a vector space for a vector with 3 elements is 0, 0, 0. Notations are used to represent the vector norm in broader calculations, and the type of vector norm calculation almost always has its unique notation. We're going to take a look at a few common vector norm calculations used in machine learning in the next lesson, and we're going to start off with the vector L1 norm. Hello and welcome back. In this lesson and the next few, we're going to talk about matrices and matrix arithmetic for machine learning. Matrices are the foundation element of linear algebra. Matrices are used throughout the field of machine learning in the description of algorithms and processes such as the input variable x when training an algorithm. In this lesson, you're going to discover matrices in linear algebra and how to manipulate them in Python. We're going to divvy the lesson up. First, we're going to talk about what is a matrix. We're going to define the matrix. We're then going to cover matrix arithmetic. We're then going to touch on matrix-matrix multiplication, called the dot product. We're also going to delve into matrix vector multiplication. And then lastly, we're going to cover matrix scalar multiplication. All right, so what is a matrix? A matrix is a two-dimensional array of scalars with one or more columns and one or more rows. The notation for a matrix is often the uppercase letters, such as an A. And entities are referred to by their two-dimensional subscript of a row, I, or the column J, such as Aij, shown with the example on screen. It's more common to see matrices defined using a horizontal notation, again as shown on screen. A likely first place you may encounter a matrix in machine learning is in model training data comprised of many rows and columns, and often represented using the capital X. The geometric analogy used to help understand vectors and some of their operations does not hold with matrices. Further, a vector itself may be considered a matrix with one or more or multiple rows. Often the dimensions of a matrix are denoted with a m or n, a lowercase, for the number of rows and the number of columns. Alright, now we know what a matrix is. Let's go ahead and define that matrix in Python. Alright, let's go ahead and define a matrix. We can represent a matrix in Python using a two-dimensional NumPy array. A NumPy array can be constructed given a list of lists. For example, on screen, we have a 2-row, 3-column matrix. When we execute the code, we get a created matrix showing the expected structure. Alright, let's move on to matrix arithmetic. Two matrices with the same dimensions can be added together to create a third matrix. The scalar elements in the resulting matrix are calculated as the addition of the elements in each of the matrices being added. We can also show it another way. We can implement this in Python using the plus operator directly on the two NumPy arrays. The example defines two 2x3 matrices and then adds them together. When we execute the code, it first prints the two parent matrices and then the result of adding them together. We can do something very similar with subtraction. One matrix can be subtracted from another matrix with the same dimensions. The scalar elements in the resulting matrix are calculated as the subtraction of the elements in each of the matrices. Again, we can show that a different way. It's a lot more verbose. We can implement this in Python using the minus operator directly on the two NumPy arrays. The example first defines 2x3 matrices and then subtracts one from another. When we execute the code, it prints out the two parent matrices and then subtracts the first matrix from the second. Alright, let's work through some matrix multiplication, called the Adamard product. Yes, I'm pronouncing that correctly. I looked it up. Two matrices with the same size can be multiplied together, and this is often called element-wise matrix multiplication, or the Adamard product. It's not a very typical operation meant when referring to matrix multiplication. Therefore, a different operator is used, such as a circle. As with element-wise subtraction and addition, element-wise multiplication involves the multiplication of elements from each parent matrix to calculate the values in the new matrix. We have that shown on screen, and we can also put it in a more verbose way. We can implement this in Python using the star operator directly on the NumPy arrays, again, as shown on screen. This defines two 2x3 matrices and then multiplies them together. When we execute the code, it first prints the two parent matrices and then the result of multiplying them together, or the Adamard product. We can also do some matrix division. One matrix can be divided by another matrix with the same dimensions. The scalar elements in the resulting matrix can be calculated as the division of the elements in each of the matrices. Again, we can put it in a more verbose way. We can also implement this in Python using the division operator directly on the two NumPy arrays. Again, our example is on screen, and it defines two 2x3 matrices and then divides the first from the second matrix. When we execute the code, it first prints the two parent matrices and then divides the first matrix by the second. Hello and welcome back. Now let's talk about matrix-matrix multiplication, or something called dot product. Matrix multiplication, also called matrix dot product, is more complicated than the previous operations, as not all matrices can be multiplied together. The rule for matrix multiplication is as follows. The number of columns n in the first matrix, A, must be equal to the number of rows m in the second matrix, B. For example, matrix A has the dimensions m rows and n columns, and matrix B has the dimensions n and k. The n columns in A and the n rows in B have to be equal. The result of the new matrix, with m rows and k columns, is shown on screen. The rule applies for a chain of matrix multiplications where the number of columns in the matrix in the chain must match the number of rows in the following matrix of that chain. The intuition for matrix multiplication is that we're calculating the dot product between each row in the matrix A for each column in the matrix B. For example, we can step down rows of column A and then multiply each with column 1 or B, give the scalar values in column 1 of C. Now, this image from Wikipedia probably makes it a little more lucid. Might help to study that for a second. You get an aha moment. The pic on screen describes the matrix multiplication using the matrix notation. This can be further simplified by removing the multiplication signs as follows. We can describe the matrix multiplication operation using an array notation, again the verbose method as shown on screen. The matrix multiplication operation can be implemented in NumPy using the dot function. Our example on screen defines two 2x3 matrices and then calculates the dot product. When you run the code, it first prints the two parent matrices and then the result of the dot product. Hello and welcome back, and let's wrap this up talking about matrix scalar multiplication. A matrix can be multiplied by a scalar. This can be represented using the dot notation between the matrix and the scalar as shown on screen, or without the dot notation, also shown on screen. The result is a matrix with the same size as the parent matrix, where each element of the matrix is multiplied by the scalar value, again as shown on screen, or as again shown on screen. We can also represent this with array notation, the verbose way. This can be implemented directly in Python with the multiplication operator. The example is shown on screen. We're going to define a 2x3 matrix and a scalar, and then multiples of them together. When we execute the code, it prints the parent matrix and the scalar, and then the result of multiplying them together. Hello and welcome back. We're going to move on to matrix operations for machine learning. Matrix operations are used in the description of machine learning algorithms. Some operations can be used directly to solve key equations, where others provide useful shorthand or a foundation in the description and the use of more complex matrix operations. In this lesson and the next few, we're going to learn about linear algebra and matrix operations. This lesson and the next few are going to be broken down into 5 disparate parts. Number 1, transpose. Number 2, inversion. Number 3, trace. Number 4, determinant. And then number 5, rank. A defined matrix can be transposed, which creates a new matrix with the numbers of columns and the rows flipped. This is denoted by the superscript T next to the matrix. An invisible diagonal line can be drawn through the matrix from top left to the bottom right, on which the matrix can be flipped to give a transpose. The operation has no effect if the matrix is symmetrical, i.e. has the same number of columns and rows and the same number of values at the same locations on both sides of the invisible diagonal line. We can transpose a matrix in NumPy by calling the T attribute. We have an example on screen, and when we run the code, it first prints the matrix as it's defined, then the transpose version. The transpose operation provides a short notation used as an element in matrix operations. All right, next up, we're on to inversion. Matrix inversion is a process that finds another matrix that, when multiplied with the matrix, results in an identity matrix. Given matrix A, find matrix B such that AB, or BA, equals N. The operation of inverting a matrix is indicated by a -1 superscript next to the matrix. For example, A superscript 1, -1, as shown on screen. The result of the operation is referred to an inverse of the original matrix. The matrix is invertible if there exists another matrix that results in the identity matrix, where not all matrices are invertible. A square matrix that is not invertible is referred to as a singular. The matrix inversion operator is not computed directly, but rather the inverted matrix is discovered through a numerical operation, where a suite of efficient methods may be used, often involving forms of matrix decomposition. A matrix can be inverted in NumPy using the inv function. Firstly, we're going to define a 2x2 matrix and then calculate the inverse of that matrix, and then confirm that inverse by multiplying it with the original matrix to give the identity matrix. When we execute the code, it prints the original, the inverse, and then the identity matrices. Matrix inversion is used as an operation involving systems and equations framed as a matrix equation, where we're interested in finding vectors of unknowns. A good example is finding a vector or a coefficient value in linear regression. Hello, welcome back. Let's go ahead and knock off trace. A trace of a square matrix is the sum of the values on the main diagonal of a matrix, top left to bottom right. The operation of calculating the trace on a square matrix is described using the notation TR of A, where A is the square of the matrix on which the operation is being performed. The trace is calculated as the sum of the diagonal values. For example, in the case of a 3x3 matrix, the trace is shown on screen, and we can also do it in array notation if you'd like. We can calculate the trace of a NumPy matrix using the, you guessed it, yet another function, because Python is all about functions, the trace function, as shown on screen. Firstly, we've got a 3 by 3 matrix, and it is created, and then the trace is calculated. When we execute the code, the first array is printed, and then the trace. Alone, the trace operation is really not that interesting, but it offers a simpler notation, and it's used as an element in other key matrix operations. Alright, let's go ahead and do determinant also in this lesson. The determinant of a square matrix is a scalar representation of the volume of a matrix. It's denoted by the det A, where A is the matrix on which we are calculating the determinant. The determinant of a square matrix is calculated from elements of the matrix. The intuition for the determinant is that it describes the way the matrix will scale other matrices when they are multiplied together. For example, a determinant of 1 preserves the space of the matrix. A determinant of 0 indicates the matrix can't be inverted. In NumPy, a determinant of a matrix can be calculated using the det function. Again, on screen we have a 3 by 3 matrix. That's how we've defined it. Then the determinant of the matrix is calculated. When we execute the code, it first prints the defined matrix and then the determinant of that matrix. Like the trace operation, alone, the determinant operation is really not that interesting, but it does offer a simpler notation and is used as an element in other matrix operations. Alright, let's wrap this up by talking about matrix rank. The rank of a matrix is the estimate of the number of linearly independent rows or columns in the matrix. The rank of a matrix M is often denoted with the function rank. An intuition for rank is to consider the number of dimensions spanned by all the other vectors within a matrix. For example, a rank of 0 suggests all vectors span one point. A rank of 1 suggests all vectors span a line, and a rank of 2 suggests all vectors span two-dimensional plane. The rank is estimated numerically, often using a matrix decomposition method. A common approach is to use singular value decomposition. NumPy again provides the matrix rank function for calculating the rank of an array. It uses the SVD method to estimate the rank. In our example one below, we're calculating the rank of a matrix with scalar values and another vector with all 0 values. When we execute the code, it first prints the vector and its rank of 1, followed by a second 0 vector and its rank of 0. The next example makes it clear that the rank is not a number of dimensions in the matrix, but a number of linearly independent directions. On screen, we have 3 examples of a 2 by 2 matrix for demonstrating the matrices of rank 0, 1, and 2. When we execute the code, it first prints out a 0, a 2 by 2 matrix, followed by the rank, then a 2 by 2 with a rank 1, and then finally a 2 by 2 matrix with a rank of 2. Hello and welcome back. In this lesson and perhaps the next few, we're going to talk about sparse matrices. Matrices that contain mostly 0 values are called sparse matrices, distinct from matrices where most of the values are non-zero, called dense. Large sparse matrices are common in general and especially in applied machine learning, such as a data that contains counts, data encodings that map categories to counts, and even in whole subfields of machine learning, such as natural language processing. It's computationally expensive to represent and work with sparse matrices, as though they are dense, and a great improvement in performance can be achieved by using representations and operations that specifically handle sparse matrices. In this lesson, you're going to discover sparse matrices, the issues they present, and how to work with them directly in Python. So let's define it. A sparse matrix is a matrix that is comprised mostly of 0 values. Sparse matrices are distinct from matrices with mostly non-zero values, which are referred to as dense matrices. The sparsity of a matrix can be quantified with a score, which is the number of 0 values in the matrix divided by the total number of elements in that matrix. We also have an example of a 3 by 6 sparse matrix. The example has 13 0 values and 18 elements in the matrix, giving the matrix a sparsity score of 0.7, 0.722 to be exact, or about 72%. In the next lesson, we're going to dive into problems with sparsity. Hello and welcome back. Let's continue talking about sparsity. So we have 2 big problems with sparsity: space complexity and time complexity. Let's talk about space complexity. Very large matrices require a lot of memory, and some very large matrices that we wish to work with are sparse. An example of a very large matrix that is too large to be stored in memory is a linked matrix that shows the links from one website to another. An example of a smaller matrix might be a word or a term occurrence matrix for words in a book against all the known words in English. In both cases, the matrix contained is a sparse matrix with many 0 values rather than data points. The problem with representing these matrices as dense matrices is that memory is required and must be allocated for each 32-bit or even 64-bit 0 value in the matrix. This is clearly a waste of memory resources, and those 0 values do not contain any information. Next up, we have something called time complexity. Assuming that a very large sparse matrix can fit into memory, we need to perform operations on it. Simply, if a sparse matrix contains mostly zero values, no data, then performing operations against it is going to take a long time, where the bulk of the computation performed will be involved adding or multiplying zero values together. This is a problem of increased time complexity of matrix operations that increases the size of the matrix. The problem is compounded when we consider that even trivial machine learning methods may require many operations on each row, column, or even across the entire matrix, resulting in vastly longer execution times. All right, let's talk about sparse matrices in Python. SciPy provides tools for creating sparse matrices using multiple data structures, as well as tools for converting a dense matrix to a sparse matrix. Many linear algebra NumPy and SciPy functions that operate on NumPy arrays can transparently operate on SciPy sparse arrays. Furthermore, machine learning libraries that use NumPy data structures can also operate transparently on SciPy sparse arrays, such as scikit-learn for general machine learning and Keras for deep learning. A dense matrix stored in a NumPy array can be converted into a sparse matrix using the CSR representation by calling the, you guessed it, CSR matrix function. In our example on screen, we're going to define a 3x6 sparse matrix as a dense array. We're going to then convert it to a CSR sparse representation, and then convert it back to a dense array by calling the toDense function. When we execute the code, it first prints the defined dense array, followed by the CSR representation, and then reconstruct it as a dense matrix. NumPy does not provide a function to calculate the sparsity of the matrix. Nevertheless, we can calculate it easily by finding the density of the matrix and then by subtracting it from 1. The number of non-zero elements in a NumPy array can be given to or provided to the count_to_non_zero function, and then the total number of elements in the array can be given by the size of the property of the array. On screen, we have an example that shows how to calculate the sparsity of an array. When we execute the code, it first prints the defined matrix followed by the sparsity of the matrix. All right, let's talk about sparse matrices in machine learning. Sparse matrices turn up a lot in applied machine learning. For example, in data. Sparse matrices come into specific types of data, most notably observations that record the occurrence or count of an activity. Some examples include whether or not a user has watched a movie in a movie catalog, whether or not a user has purchased a product in a product catalog, and lastly, the count of the number of listens of a song in a song catalog. Next up, there's data preparation. Sparse matrices come into encoding schemes used in the preparation or the cleansing of data. Some examples include one-hot encoding, which is used to represent categorical data as sparse binary vectors, count encoding, which is used to represent the frequency of words in a vocabulary of a document, TF-IDF encoding, which is used to represent normalized word frequency scores in a vocabulary. All right, next up, we're going to look at sparse matrices in Python. A lot of linear algebra is concerned with operations on vectors and matrices, and there are many different types of matrices. There are a few types of matrices that you may encounter again and again when getting started in linear algebra, particularly the parts of linear algebra relevant to machine learning. In this lesson, and the next few, you're going to discover a suite of different types of matrices from the field of linear algebra that you're going to encounter or you may encounter in machine learning. We're going to talk about square matrices, symmetric matrices, triangular ones, diagonal ones, identity matrices, and orthogonal matrices. All right, up first is a square matrix. A square matrix is a matrix where the number of rows equals the number of columns. N is equal to M. The square matrix is contrasted with the rectangular matrix, where the number of rows and columns are not equal. Given that the number of rows and columns match, the dimensions are usually denoted as n, for example, n and n. The size of the matrix is called the order. So an order of 4 square matrices is a 4x4. The vector of values along the diagonal of the matrix, from the top left to the bottom right, is called the main diagonal. On screen, we have an example of an order 3 square matrix. Square matrices are readily added and multiplied together, and are the bases of many simple linear transformations, such as rotations, as used in the rotation of images. Next up, we have the symmetric matrix. A symmetric matrix is a type of square matrix where the top right triangle is the same as the bottom left triangle. To be symmetric, the axis of symmetry is always the main diagonal of the matrix, from top left to bottom right. On screen, we have an example of a 5x5 symmetric matrix. A symmetric matrix is always square and equal to its transpose. Hello and welcome back. Now let's talk about the triangular matrix. A triangular matrix is a type of square matrix that has all values in the upper right or lower left corner of the matrix, with the remaining elements filled with 0 values. A triangular matrix with values only above the main diagonal is called an upper triangular matrix, whereas a triangular matrix with values only below the main diagonal is called a lower triangular matrix. On screen, our first example is a 3 by 3 upper triangular matrix. Just below that on screen is a 3 by 3 lower triangular matrix. The LU decomposition resolves a given matrix into upper and lower triangle matrices. NumPy provides functions to calculate a triangular matrix from an existing square matrix. The trill function can calculate the lower triangular matrix from a given matrix, and the TreeU to calculate the upper function triangular matrix from a given matrix. Our example on screen defines a 3 by 3 matrix and then calculates the lower and upper triangular matrix from it. When you execute the code, it first prints out the matrix, followed by the lower and the upper triangular matrices. Next up, we have the diagonal matrix. A diagonal matrix is one where the values outside of the main diagonal have 0 values, where the main diagonal is taken from the top left of the matrix to the bottom right. A diagonal matrix is often denoted with the variable d, and may be represented as a full matrix or as a vector of values on the main diagonal. On screen is an example of a 3 by 3 square diagonal matrix. As a vector, we would represent it as, again showed on screen, or with specified scalar values. A diagonal matrix does not have to be square. In the case of a rectangular matrix, the diagonal would cover the shortest dimension. Example on screen. NumPy provides the diag function that can create a diagonal matrix from an existing matrix or transform a vector into a diagonal matrix. The example on screen defines a 3 by 3 square matrix, extracts the main diagonal as a vector, and then creates a diagonal matrix from the extracted vector. When we execute the code, it first prints the defined matrix, followed by the vector of the main diagonal, and the diagonal matrix constructed from the vector. Alright, let's talk about the identity matrix. An identity matrix is a square matrix that does not change a vector when multiplied. The values of an identity matrix are known. All of the scalar values along the main diagonal from top left to bottom right have the value of 1, while all the other values have a 0. An identity matrix is often represented using the notation I, or with the dimensionality, n, where n is the subscript that indicates the dimensionality of the square index matrix. In some notations, the identity may be referred to as a unit matrix, or U, to honor the one value it contains. This is different from the unitary matrix. On screen, an identity matrix with the size of 3, or I3, would be as follows. In NumPy, an identity matrix can be created with a specific size, using the identity function. The example on screen creates a I3 identity matrix. When we execute the code, it prints out the identity matrix. Alone, the identity matrix is not that interesting, although it's a component in other important matrix operations. Alright, let's lastly touch on an orthogonal matrix. Two vectors are orthogonal when their dot product equals 0, called orthonormal, which is shown on screen. This is intuitive when we consider that one line is orthogonal with another if it is perpendicular to it. An orthogonal matrix is a type of square matrix whose columns and rows are orthogonal unit vectors, i.e. they're perpendicular and have a length or magnitude of 1. An orthogonal matrix is defined as, again, the equation shown on screen, where Q is the orthogonal matrix and Q of (T) indicates the transpose of Q, and I is the identity of the matrix. A simple 2 by 2 orthogonal matrix is listed below, which is an example of a reflection matrix or a coordinate matrix. On screen is an example of an orthogonal matrix. When we execute the code, it first prints out the orthogonal matrix, the inverse of the orthogonal matrix, and the transpose of the orthogonal matrix, and then printed and are shown to be equivalent. Finally, the identity matrix is printed, which is calculated from the dot product of the orthogonal matrix with the transpose. Orthogonal matrices are useful tools as they are computationally cheap and stable to calculate their inverse, as simply their transpose. Hello and welcome back. It's on to tensors for machine learning with NumPy. In deep learning, it's common to see a lot of discussions around tensors as the cornerstone data structure. Tensors appear in the name of Google's flagship machine learning framework called TensorFlow. Tensors are a type of data structure used in linear algebra, and like vectors and matrices, you can calculate arithmetic operations with tensors. In this lesson and the next few, you're going to discover what tensors are and how to manipulate them in Python with NumPy. We're going to break down the section into what are tensors, then we'll talk about tensors in Python, and then we'll talk about element-wise tensor operations, and we'll talk about tensor product. So, what is a tensor? A tensor is a generalization of vectors and matrices, and it's easily understood as a multidimensional array. A vector is a one-dimensional of the first-order tensor, and a matrix is a two-dimensional of the second-order tensor. Tensor notation is much like matrix notation, with a capital letter representing a tensor and a lowercase letter with a subscript integer representing scalar values within that tensor, as shown on screen. Many of the operations that can be performed on scalars, vectors, and matrices can also be performed on tensors. As a tool, tensors or tensor algebra is widely used in the field of physics and engineering. It is a term and a set of techniques known in machine learning in the training and operation of deep learning models, and can be described in terms of tensors. All right, let's talk about tensors in Python. Like vectors and matrices, tensors can be represented in Python using n-dimensional arrays, or the ND array. A tensor can be defined in line to the constructor of an array as a list of lists. The example on screen defines a 3x3x3 tensor as a NumPy array. 3 dimensions is easy to wrap your head around. First, we define the rows, then a list of rows stacked as columns, then a list of columns stacked as levels in a cube. When we execute the code, it first prints the shape of the tensor, then the values of the tensor itself. You can see that, at least in 3 dimensions, the tensor is printed as a series of matrices, one for each layer. For this 3D tensor, axis 0 specifies the level, axis 1 specifies the row, and the axis 2 specifies the column. All right, let's talk about some element-wise tensor operations. As with matrices, we can perform element-wise arithmetic between tensors. Let's talk about tensor addition. The element-wise addition of 2 tensors with the same dimension results in a new tensor with the same dimensions where each scalar value is the element-wise addition of the scalars in the parent tensor. In NumPy, we can add tensors directly by adding arrays, as shown on screen. When we execute the code, it prints the addition of the 2 parent tensors. Next up, we have tensor subtraction. The element-wise subtraction of one tensor from another with the same dimensions results in a new tensor with the same dimensions where each scalar value is the element-wise subtraction of the scalars in the parent tensor. In NumPy, we can subtract tensors directly by subtracting arrays. When we execute the code, it results in the subtraction of the first tensor from the second. Welcome back. Let's talk about tensor product. The tensor product operation is often denoted as a circle with a small x in the middle. We're going to note it here with an x. Given a tensor A with q dimensions and tensor B with r dimensions, the product of these tensors will be a new tensor with the order of q plus r, or, said another way, q plus r dimensions. The tensor product is not limited to tensors, but can also be performed on matrices and vectors, which can be good to practice with in order to develop an intuition for higher dimensions. Let's take a look at a tensor product for vectors. We can define it on screen, then we can unroll it. Then we can take a look at a tensor product for matrices, and then we can unroll it. The tensor product can be implemented in NumPy using the tensor dot function. The function takes as arguments the 2 tensors to be multiplied and the axis on which the sum of the product's over, called the sum of reduction. To calculate the tensor product, also called the tensor dot product in NumPy, the axis must be set to 0. In our example on screen, we're going to define 2 order 1 tensor vectors and then calculate the tensor product. When we execute the code, it prints the results of the tensor product. The result is an order 2 tensor matrix with a length of 2 by 2. The tensor product is the most common form of tensor multiplication that you're going to encounter, but there are many other types of tensor multiplications that exist, such as tensor dot product and the tensor contraction. In this lesson and the next few, let's talk about matrix factorization for machine learning. Many complex math operations cannot be solved efficiently or with stability using the limited precision of computers. Matrix decompositions are methods that reduce a matrix into its constituent parts that make it easier to calculate more complex matrix operations. Matrix decomposition methods, also called matrix factorization methods, are a foundation of linear algebra in computers, even for basic operations such as solving systems of linear equations, calculating the inverse, and calculating the determinant of a matrix. In this lesson, you're going to discover matrix decompositions and how to calculate them in Python. As always, we're going to break it down into 4 disparate parts. Firstly, what is matrix decomposition? Secondly, LU matrix decomposition. Thirdly, QR matrix decomposition. And fourthly, Cholesky decomposition. All right, let's define it. What is matrix decomposition? A matrix decomposition is a way of reducing a matrix into its constituent parts. It's an approach that you can simplify more complex matrix operations that can be performed on the decomposition matrix rather than on the original matrix itself. A common analogy for a matrix decomposition is the factoring of numbers, such as the factoring of 10 into 2 by 5. For this reason, matrix decomposition is also called matrix factorization. Like factoring real numbers, there are many ways to decompose a matrix. Hence, there are a range of different matrix decomposition techniques. Two simple and widely used matrix decomposition methods are the LU matrix decomposition and the QR matrix decomposition. In the next lesson, we're going to take a closer look at these. Hello and welcome back. All right, let's tackle LU matrix decomposition. The LU matrix decomposition is for square matrices and decomposes a matrix into L and U components, as shown on screen, and then as shown again without the dot notation, where A is the square matrix that we wish to decompose, L is the lower triangle of the matrix, and U is the upper triangle of the matrix. The LU decomposition is found using an iterative numerical process and can fail for those matrices that cannot be decomposed or decomposed easily. A variation of this decomposition that is numerically more stable to solve in practice is called LUP decomposition, or the LU decomposition with partial pivoting, and that's shown on screen. The rows of the parent matrix are reordered to simplify the decomposition process, and the additional P matrix specifies a way to permute the result or the result with the results to the original order. There are also other variations of the LU. The LU decomposition is often used to simplify the solving process of linear equations, such as finding the coefficients in a linear regression problem, as well as calculating the determinant and inverse of a matrix. The LU decomposition can be implemented in Python with the LU function. More specifically, the function calculates the LPU decomposition. In our example on screen, we have a 3 by 3 square matrix. The LU decomposition is calculated, and then the original matrix is reconstructed from the components. When we execute the code, it first prints the defined 3 by 3 matrix, then the P, L, and U components of the decomposition, and then lastly, the original matrix is reconstructed. Next up is QR matrix decomposition. The QR decomposition is for M and N matrices, not limited to square matrices, and decomposes a matrix into Q and R components, as shown on screen, and then of course without the dot notation. Where A is the matrix that we wish to decompose, Q is the matrix with the size M of M, and R is the upper triangle of the matrix with the size M of it. The QR decomposition is found using an iterative numerical method that can fail on those matrices that can't be decomposed or can't be decomposed easily. Like the LU decomposition, the QR decomposition is often used to solve systems of linear equations, although it's not limited to square matrices. The QR decomposition can be implemented in NumPy using the QR function. By default, the function returns the Q and R matrix with smaller reduced dimensions that are more economical. We can change this to return the expected sizes of M and M for Q and then M and N for R by specifying the mode arguments to complete, although this is not required for most applications. On screen, we have a 3 by 2 matrix, which calculates the QR decomposition and then reconstructs the original matrix from the decomposed elements. When we execute the code, it first prints out the defined 3 by 2 matrix, then the Q and R elements, and then finally the reconstructed matrix that matches what we started with. All right, let's continue on with Cholesky decomposition. The Cholesky decomposition is for square matrices where all the eigenvalues are greater than 0, the so-called positive definite matrices. For our interest in machine learning, we're going to focus on Cholesky decomposition for real-valued matrices and ignore the cases when working with complex numbers. The decomposition is defined as follows on screen, and then without the dot notation, where A is the matrix being decomposed, L is the lower triangle of the matrix, and L of T is the transpose of L. The decomposed can also be written as the product of the upper triangle matrix as shown on screen, where U is the upper triangular matrix. The Cholesky decomposition is used for solving linear squares for linear regression, as well as simulation and optimization methods. When decomposing symmetric matrices, the Cholesky decomposition is nearly twice as efficient as the LU decomposition and should be preferred in these cases. The Cholesky decomposition can be implemented in NumPy by calling the Cholesky function. The function only returns L, as we can easily access the L transpose as needed. Our example on screen defines a 3 by 3 symmetric and positive definite matrix and then calculates the Cholesky decomposition, and then the original matrix is reconstructed. When we execute the code, it first prints the symmetric matrix, then the lower triangle matrix, and then the decomposition followed by the reconstructed matrix. Welcome back. We're going to start talking about eigenvalues and eigenvectors for machine learning. Matrix decomposition are a useful tool for reducing a matrix to their constituent parts in order to simplify a range of more complex operations. Perhaps the most widely used type of matrix decomposition is the eigen decomposition that decomposes a matrix into eigenvectors and eigenvalues. This decomposition also plays a role in the methods used in machine learning, such as principal component analysis. We're going to break this lesson in the next few into 5 disparate parts. We're going to talk about eigen decomposition of a matrix. We're going to talk about eigenvectors and eigenvalues. We're going to talk about the calculation of eigen decomposition. We're going to confirm an eigenvector, and we're going to confirm eigenvalues, and then we're going to reconstruct the original matrix. Eigen decomposition of a matrix is a type of decomposition that involves decomposing a square matrix into a set of eigenvectors and eigenvalues. A vector is an eigenvector of a matrix if it satisfies the following equation, which is shown on screen. This is called the eigenvalue equation, where A is the parent square matrix that we are decomposing, V is the eigenvector of the matrix, and lambda is the lowercase Greek letter that represents the eigenscalar. And again, we can show this without the dot notation. A matrix could have one eigenvector and one eigenvalue for each dimension of the parent matrix. Not all square matrices can be decomposed into eigenvectors and eigenvalues, and some can be decomposed in the way that requires complex numbers. The parent matrix can be shown to be a product of the eigenvectors and eigenvalues, as shown on screen, and then without the dot notation, and again as shown on screen. Where Q is a matrix comprised of eigenvectors, diag_V is the diagonal matrix comprised of the eigenvalues along the diagonal, sometimes represented with a capital lambda, and Q-1 is the inverse of the matrix comprised of the eigenvectors. Eigen is not a name. For example, the method named after eigen. Eigen, pronounced I like your I, and then eigen, is a German word that means own or innate, as belonging to the parent matrix. A decomposition operation does not result in a compression of a matrix. Instead, it breaks it down into its constituent parts to make certain operations on that matrix easier to perform. Like other matrix decomposition methods, eigen decomposition is used as an element to simply satisfy the calculation of one or more complex matrix operations. Eigen decomposition can also be used to calculate the principal components of a matrix in principal component analysis, or PCA, which is used in machine learning for reducing dimensionality. Hello and welcome back. Eigenvectors are unit vectors, which means that their length or magnitude is equal to 1.0. They are often referred to as right vectors, which simply means a column vector as opposed to a row vector or left vector. A right vector is a vector as we understand them. Eigenvalues are coefficients applied to eigenvectors that give the vectors their length or magnitude. For example, a negative eigenvalue may reverse the direction of the eigenvector as part of scaling it. A matrix that has positive eigenvalues is referred to as a positive definite matrix, whereas when the eigenvalues are all negative, it's referred to as a negative definite matrix. All right, let's look at the calculation of eigen decomposition. Eigen decomposition is calculated on a square matrix using an efficient iterative algorithm, of which we're not going to go into the details here. Often an eigenvalue is found first, and then an eigenvector is found to solve the equation as a set of coefficients. The eigen decomposition can be calculated in NumPy using the EIG function. We have an example on screen that defines a 3x3 square matrix. The eigen decomposition is calculated on the matrix returning the eigenvalues and eigenvectors. Running the example first prints the defined matrix, followed by the eigenvalues and the eigenvectors. More specifically, the eigenvectors are the right-hand side eigenvectors and normalized to unit length. We can confirm that a vector is indeed an eigenvector of a matrix. We can do this by multiplying the candidate eigenvector by the eigenvector and then comparing the result with the eigenvalue. First, we're going to need to define a matrix, then calculate the eigenvalues and eigenvectors. We're then going to test whether the first vector and value are in fact eigenvalues and eigenvectors. We know they are, but it's a good exercise. The eigenvectors are returned as a matrix with the same dimensions as a parent matrix, where each column is the eigenvector i.e. the first eigenvector is a vector. Eigenvalues are returned as a list, where the value indices in the returned array are paired with eigenvectors by the column index. For example, the first eigenvalue at 0 is paired with the first eigenvector at 0. Little confusing, but it's much easier to understand if we have an example, and that's what we have on screen. When we execute the code, it first prints the two multiplications that show the same resulting vectors, and this is what we'd expect. Next up, let's go ahead and reconstruct the original matrix. We can reverse the process and reconstruct the original matrix given only the eigenvectors and eigenvalues. First, the list of eigenvectors must be converted into a matrix, where each vector becomes a row. The eigenvalues need to be arranged into a diagonal matrix. The numpy diag function can be used for this. Next up, we need to calculate the inverse of the eigenvector matrix, which we're going to achieve with the inv function in numpy. Lastly, these elements need to be multiplied together using the dot function. When we put all this together, we have our example on screen, and it calculates the eigenvalues and eigenvectors again, and then uses them to reconstruct the original matrix. Running the example first prints the original matrix, then the matrix reconstructed from the eigenvalues and eigenvectors, matching that original matrix. Hello and welcome back. Let's go ahead and calculate SVD, or singular value decomposition, from scratch in Python. Also known as matrix factorization, involves describing a given matrix using its constituent elements. Perhaps the most known and widely used matrix decomposition method is SVD, or singular value decomposition. All matrices have an SVD, which makes it more stable than any other method, such as eigendecomposition. It's often used in a wide variety of applications, including compression, denoising, and data reduction. In this lesson, you're going to discover how to use singular value decomposition method for decomposing a matrix into its constituent parts. We're going to break down the lesson into 5 parts. Firstly, we're going to talk about singular value decomposition, and then we're going to calculate a singular value decomposition. Then we're going to reconstruct a matrix from an SVD, and then we're going to use SVD for pseudo-inverse, and then we're going to use an SVD for dimensionality reduction. The singular value decomposition, or SVD for short, is a matrix decomposition method for reducing a matrix into its constituent parts in order to make certain subsequent matrix calculations simpler. For simplicity, we're going to focus on the SVD for real-valued matrices and ignore the case for complex numbers. Our formula is seen on screen, where A is the real M and N matrix we wish to decompose. U is an M and N matrix. Sigma, often represented by uppercase Greek sigma letters, is an M and N directional matrix. And V of T is the transpose of the M and N matrix, where T is the superscript. The diagonal values of a sigma matrix are known as singular values of the original matrix A. The columns of the U matrix are called left singular vectors of A, and the right columns of V are called the right singular vectors of A. The SVD is calculated via iterative numerical methods. We're not going to go into the details now. Every rectangular matrix has a singular value decomposition, although the resulting matrices may contain complex numbers, and the limitations of floating point arithmetic may cause some matrices to fail to decompose neatly. The SVD is used widely both in the calculation of other matrix operations, such as matrix inverse, and also in the data reduction methods in machine learning. SVD can also be used in least squared linear regression, image compression, and denoising data. All right, let's see a real example of this. The SVD is calculated by calling the SVD function in Python. The function takes a matrix and returns the U, sigma, and the V of T elements. The sigma diagonal matrix is returned as a vector of singular values. The V matrix is returned as a transposed form, i.e. V of T. The example on screen defines a 3x2 matrix and then calculates the singular value decomposition for it. When we execute the code, it first prints the defined 3x2 matrix, then the 3x3 U of matrix, 2 elements of the sigma vector, and a 2x2 V of T matrix elements calculated from the decomposition. Hello and welcome back. Next up, let's reconstruct a matrix from a singular value decomposition. The original matrix can be reconstructed from the U, sigma, and the V to T elements. The U, S, and V elements returned from the SVD cannot be multiplied directly. The S vector must be converted into a diagonal matrix using the diag function. By default, this function is going to create a square matrix that is n of n relative to the original matrix. This causes a problem, as the size of the matrices do not fit the rule of matrix multiplication, where the number of columns in a matrix must match the number of rows in the subsequent matrix. After creating the square sigma diagonal matrix, the size of the matrices are relative to the original M of n matrix. that we're going to decompose, as shown on screen. The first formula is going to show what it is. The second one is going to show what we require. Now, we're going to achieve what we require by creating a new sigma matrix of all 0 values, that is m of n, i.e. more rows, and then populate it first with the n and n part of the matrix with the square diagonal matrix calculated via the diag. We put all this together as shown on screen. When we execute the code, it first prints the original matrix, then the matrix reconstructed from the SVD elements. The complication we're discussing with the sigma diagonal only exists with the case where m and m are not equal. The diagonal matrix can be used directly when reconstructing a square matrix. Again, our example is on screen. When we execute the code, it first prints the original 3x3 matrix and then the version reconstructed directly from the SVD elements. All right, let's talk about dimensionality reduction. A popular application of SVD is for dimensionality reduction. Data with large number of features, such as more features, columns, and observations, rows, may be reduced to a smaller subset of features that are the most relevant to the prediction problem. The result is a matrix with a lower rank that is said to approximate the original matrix. To do this, we can perform an SVD operation on the original data and then select the k largest singular values in sigma. These columns can be selected from sigma and the rows selected from v of t. An approximate b of the original vector a can be reconstructed as shown on screen. In natural language processing, this approach can be used on matrices of word occurrences or word frequencies in documents, and is called latent semantic analysis or latent semantic indexing. Now in practice, we can retain and work with the descriptive subset of the data called T. This is a dense summary of the matrix or a projection. Further, this transform can be calculated and applied to the original matrix A, as well as other similar matrices. The example on screen demonstrates data reduction with an SVD. First, a 3x10 matrix is defined, with more columns than rows. The SVD is calculated, and only the first 2 features are selected. The elements are then recombined, and then given an accurate reproduction of the original matrix. Lastly, a transform is calculated in 2 different ways. When we execute the code of our example on screen, it first prints the defined matrix, and then the reconstructed approximation, followed by 2 equivalent transforms to that original matrix. Scikit-learn provides a truncated SVD class that implements this capability directly. The truncated SVD class can be created, in which you must specify the number of desirable features of the components to select. For example 2, once created, you can fit the transform by calling the fit function, and then apply it to the original matrix by calling the transform function. Our example on screen demonstrates the truncated SVD class. When we execute the code, it first prints the defined matrix, followed by the transform version of that matrix. We can see that the values match those calculated manually, except for the sign on some values. We can expect there to be some instability when it comes to the sign, given the nature of the calculations involved and the difference of the underlying libraries and methods used. The instability of signs shouldn't be a problem in practice, as long as the transform is trained for reuse.